Okay, so my name is Frank Wattenberg. I'm from the Department of Mathematical Sciences at the United States Military Academy at West Point. The work I'm going to talk about today is joint work with actually a number of people, but in particular Major Matt Mogensen, also at the United States Military Academy in the Department of Mathematical Sciences. And you can see our email addresses, and we'd be delighted to hear from you and talk more about this. This is the obligatory disclaimer. The views we're talking about here are our own views. They don't necessarily reflect those of the United States Military Academy, the United States Army, or the United States government. What we're going to talk about is one very big topic, and that's robotics and artificial intelligence, and particularly using robotics and artificial intelligence as an interdisciplinary topic cutting across a number of different courses, and really a topic that can help unify our students' academic experience. That topic is important for 4 reasons. In fact, we choose that topic for 4 reasons. The first one is its importance. We live in an age where we are increasingly using robots, and robots imbued with artificial intelligence, and it's really going to change the way we are. It's going to change what our lives are like, and it's very important. Our students now, the ones in our classrooms, are the ones who are going to shape their future, and the more they know about science and actually economics, law, all kinds of things, the more likely they are to change our world for the better. The other thing is that this is a topic that is particularly urgent. People don't realize the extent to which we are already using artificial intelligence to make decisions that are usually made or formally made by people. The third reason is it's essentially an interdisciplinary topic. To make any progress on this, you really have to know a lot about everything. All the STEM disciplines, science, technology, engineering, and mathematics, those are the disciplines that are going to make this happen. They're going to determine what we can do. But we need to know economics, for example, because if we, for example, go to robotic cars, we're going to put a lot of cab drivers out of work, and we need to know the economic consequences of those kinds of decisions. We need to know about history. This is essentially a disruptive technology, and we can learn a lot about disruptive technologies by looking at other disruptive technologies in the past history. Another topic I want to mention is intellectual integrity. One of the things that this is particularly good for is it's particularly good for teaching us and our students to be very careful, to be very tenacious in making sure we've really solved a problem. It's not good enough to get an 80% solution or a 90% solution. We really want a solution where we understand the consequences, we understand the assumptions that are underlying that, we understand the sensitivity of what we've built to changes in condition. So our goal today is twofold. First of all, we're going to do some hands-on. We're actually going to build a little robot. Actually, UC is going to build a little robot. And we're also going to discuss some of the very general principles involved in artificial intelligence and robotics. So here is one of the delightful things about this topic is every day you are going to get 3 or 4 email alerts with a headline that's relevant. So here's one that appeared in my email box, I think 2 or 3 days ago. It's from Consumer Reports, and I'll read it. It says, in yet another bid to maximize profits, some insurance companies have begun in the past few years to use a new technique to determine your sensitivity to prices. Now their basic goal here is they want to charge you as much as you're willing to pay. And you think that what most of us would conceive as a fair price for insurance would be based on our driving record. How likely are we to get in an accident? How likely are we to make claims? But in fact, they're using a lot of other information. Some of the information they're using, for example, is based on your credit score. Apparently, credit score is, for them, a reasonable predictor of what they're going to cost you. There's another technique that's a little scarier. It's called price optimization. It's being used not only in the insurance industry, but other places. And their goal is to charge you the price that you in particular are willing to pay. Now, there's an awful lot of information about you out there. For example, when you shop, if you use a shopper's card, there's information out there about what you buy. And for example, if you habitually buy higher priced products, it's reasonable to conclude that you're not very price sensitive. So someday you may find yourself paying more because you have been buying things that are more expensive. So that's one example of how artificial intelligence and decision making on the basis of these algorithms is impacting your life. One of the most interesting things about this is at United States Military Academy, for example, the Department of English is very, very interested. And one of the reasons they're interested in this is if you want to see some of the most interesting thinking about a world with artificial intelligence and a world with robots, a good place to look is science fiction. So the classics are a 3-book trilogy by Isaac Asimov called the Robot Trilogy. First one's called The Caves of Steel, The Naked Sun, Robots at Dawn. Highly recommend it. One of my summer projects was to read a bunch of science fiction, and it's really entertaining. In particular, Asimov's 3 laws are famous. These are the 3 laws that he formulated to govern the activity of, in this case, often humanoid robots, but very intelligent robots. In addition, if we want to talk to people about the impact of artificial intelligence, about robotics, science fiction is a good venue in which to do that, because we can write stories that convey on a personal level what's going to happen. It's not just PowerPoint slides, it's getting immersed in a story. So now we're going to switch a little bit, and we're going to talk about another aspect. One of the things we're doing is we're experimenting with actually having our cadets build some robots, do some programming. And you've got a slide in front of you, this ties into something called the maker movement. The maker movement is incredibly exciting. There's lots and lots of people doing lots of things that they're building themselves. If you have an opportunity to go to a maker fair in your area, I highly recommend it. My favorite example is I went to a maker fair in New York City, and there were a group of students who looked at a common problem in Africa, which is that kids often have to walk 2 or 3 miles to get water. When they get the water, it's not very good water, but it's water. And then they have to walk 2 or 3 miles back to bring the water back home, often balancing that water on their heads. It's not fun, it's not good for them. When they get back, the water isn't necessarily very good. So these kids had, what would happen if we built something that was a little like a volleyball? And they did. And what they do is you fill this volleyball-like thing up with water, and instead of carrying this back on your head, you kick it home. And as you kick it home, it's designed so that the water goes through a system of filters. And so at the same time, you're maybe having a little bit more fun. It's a little bit easier on your head and neck than if you were carrying the water on your head. And in addition, you're actually purifying the water. Now, I'm not sure whether that's ever going to be widely deployed in Africa, but the exciting thing is 3 kids could build one of these and test it out themselves. And that's what the maker movement is all about. If you go to a maker fair, what you'll discover is there's everything from people doing quilts, people doing woodcraft, often using classical tools, often using antique tools, to people using 3D printing machines, and you'll see a lot of people doing electronic stuff with things like the Arduino, which is what we're going to use. So by involving our students in doing this, what we expect is students who are going to be more resourceful, more agile, more able to tinker. So given a problem, if they've got a tool that doesn't quite fit, they can make it better, they can make it fit. I mentioned intellectual integrity and rigor before. That's incredibly important when you're building things, because when you're building something, you can't just build something that works sitting in your workshop. You've got to build something that's going to be able to work out in the real world. So that requires a kind of a tenacity, a kind of attention to detail. It's fun. I mean, this is really, really fun. And that's always important. It's nice when you're working, you can have some fun. And finally, we're at a stage right now with robotics that's very similar to the stage we were with when the Apple II computer came out, and the TRS-80 and some of the early computers. At that time, an Apple II computer cost about $1,200 when it first came out. That's about $5,000 in current dollars. There were lots of computers. Government had computers, big business had computers, scientists were using computers. We're at the same situation now with robotics. There are lots of robots out there, and generally they're expensive, and they're being used to do all sorts of cool things. But now, we're going to talk about roughly $300 or $350 worth of equipment that you can buy, your students can buy, that will give them essentially a personal robotics library that's every bit as good as the personal computer was 25 years ago. So the adventurers, the tinkerers, the inventors that were working in their garages, their parents' garages 25 years ago. They're probably still in the garage, but now they're building robots. So up on the upper left corner, you'll see a picture of something called a Sparky. And that's a little robot that's very cool. It's designed primarily for kids aged 9 and above. And I really call your attention to that ages 9+ on the box. With this little robot, you can do lots of things. You can program it. So kids that are 9 can program. You can do it using a visual programming environment, which is very easy. But you also do it using kind of a simple subset of C. And students will do that. So it's exciting. So this is very, very accessible. So you may, if you start talking about doing this, you may encounter some resistance from people that say it's too hard. It's not too hard for 9-year-olds. It's not too hard for our students right now. The heart of what we're going to do is something called an Arduino Uno. Now what it's got is, and you're looking at one now, there's a microprocessor, and it's just a little tiny computer. You can program it. It does all the things that computers do. What's more important is it's got a whole bunch of little things called ports. And those little ports allow it to communicate with the outside world. So we use those ports to get information from sensors. We use that ports to do things like turn motors on or decide how fast motors go to turn lights on and off. So that's the Arduino Uno. I actually recommend something called an Arduino starter kit. So especially if you've got kids that are 11 or 12 years old, even 10, depending on the kids, you can actually buy this for under $100. It's available at Amazon.com. It's got that Arduino Uno in it, but it's also got a really nice collection of parts. There are some things that do things, some motors, some lights you can turn on, things that make noises. It's got sensors, temperature sensors, light sensors, all kinds of things. So you can, and probably the most important thing is it's got a really nice manual. So this is a manual that kids can go through, they can learn on their own. In addition, there's an awful lot of information available on the web. So another favorite supplier I have is a company called Adafruit. That's Adafruit. And if you go to adafruit.com or Google them and explore their website, you'll find that they sell a whole bunch of interesting parts. What's more important is they provide really interesting tutorials and documentation. There's a lot of information out there. We're going to do it in a minute. Yuxi is going to build a little robot. She's not actually going to build a robot. If in a class, the students would start out with a little kit that's basically a collection of miscellaneous parts and costs about $150, and they would build what you see in front of you. What Yuxi is going to do is do a step that would occur a little bit later. She's going to add something to that, one of the sensors we were talking about. So this is the start. When she's done, she's going to have something that looks like this. And on the front of this, you'll see something that looks like a pair of eyes, which one of the neatest things about it. Looks like it's a pair of eyes. It's actually not a pair of eyes. What it is a device. It's a sonar unit. It will send out a sound pulse. And it times how long that sound pulse takes to go out, hit some kind of an obstacle, be echoed back, bounce back, and be received. So based on how long it takes that sound pulse to go, it knows how far away, or it can be programmed to know how far away the object is. So for example, suppose you wanted to build just a little piece of a self-driving car for your own use. You'd probably want to have it have the capability of driving into your garage and stopping maybe 10 inches from the back wall. The way you do that is you'd put some kind of an ultrasonic detector like this in front of it, and then you'd program that. So that's our goal. So I'm going to just very quickly put a little bit of code up. We don't have time to talk about code, but this will give you some idea of what's involved in programming. You'll notice up at the top, there's two things that say define trig pin and define echo pin. What that means is I'm going to use two of those ports, port 6 and 7, to connect the trigger pin and the echo pin to connect the trigger and echo function essentially on that ultrasonic rangefinder to the Arduino. So the Arduino is going to send information to the rangefinder and then receive information back from those two pins. Those two numbers are going to come up in a few minutes. Then you'll see something called float get time. And what that is a little routine that does two things. It sends a signal out to the ultrasonic rangefinder that essentially send that sound out, trigger that sound pulse, and then it waits until the echo comes back, the return comes back, and then it returns how long that was. So that's essentially what we need, essentially, to build our self-parking in a simple garage situation device. Okay. Okay, so UXI is going to use 5 parts. The first part is the ultrasonic rangefinder that we talked about. I'll get it to UXI. And she's going to put that on the front of the robot. And she's using 4 pins, and those 4 pins actually perform a physical function. They actually hold the ultrasonic unit in place. But in addition, they provide some electrical contacts that we're going to use to make connections between the ultrasonic rangefinder and the Arduino Uno that's the brains behind this object. Now she's also going to use 4 wires. The first wire is a black wire, and this black wire is going to establish a connection. It's one of 2 wires actually, that one is red, that are going to establish a power connection between the ultrasonic rangefinder and the Arduino Uno. What she's doing now is she's connecting one end essentially to the ground pin on the rangefinder and the other end to the ground pin on the Arduino Uno. And now she's going to use a red wire to establish the connection between the VCC pin on the ultrasonic rangefinder and the 5-volt pin on the Arduino Uno. And now I mentioned there is a trigger and an echo signal. The next thing we're going to do is we're going to establish a connection. We're going to use a yellow wire to establish a connection between the echo pin on the ultrasonic rangefinder and pin number digital 7 or D7 on the Arduino Uno. And if you remember in the computer code, the echo pin was pin number D7. And then we'll do the same thing using a blue wire to establish a connection between the trigger pin and digital pin number 6. Okay, so our robot has limited eyes, look like eyes, but actually all it does is measures sound, and we're going to use it as a rangefinder, and we'll just plug it in to get some power, and we'll turn it on. There's a little switch over here. Oh, I guess it was on. And now you can see how it works by holding her hand as a target and putting it in front of the thing. I'll press the button because she doesn't have 2 hands. And it took 531 microseconds for the sound waves to go from that ultrasonic rangefinder to her hand and back. Cool. Okay, so we're going to use 4 parts in this construction. The first part on the top is this ultrasonic rangefinder I talked about, and then the other 4 parts are just wires. These wires have 4 different colors just to keep them straight. There's no physical significance to those colors. When you start, the first thing we're going to do is we're going to put that ultrasonic rangefinder at the very front of the robot with what looks like eyes facing forward. So you insert the 4 pins of the ultrasonic rangefinder into 4 holes as shown. And when we're done, we're going to have the 4 wires making these connections. So what you're seeing here is from left to right, there's a black wire that goes in the same column, and all the holes in that column are electrically connected to each other. In the same column as the ground pin on the ultrasonic rangefinder, and it goes over into one of the ground pins over on the right. Then there's a yellow wire, a blue wire, and a red wire, and those 3 wires also establish connections. I'll talk a little bit more about that in a minute. In fact, these are kind of out of order. Here's a close-up that gives you a better picture of what you're doing. Surrounding the breadboard, you'll see some holes and some black things. The breadboard is going to be make connections between things. Notice at the upper left, you'll see 5 holes labeled 5 volts. Those go to a port on the Arduino Uno that supplies 5 volts of positive. In the lower right, you'll see pins that say ground. And those pins are connected to the ground on the Arduino Uno. Then you'll see pins on the bottom that are labeled from left to right, 13, 12, 11, 10. Those are digital pins, and we're going to use those as well. So those pins, the black pins, the black holes, are connected to the Arduino Uno. So what we've done up here is we basically established connections between the ultrasonic rangefinder and the Arduino Uno. So here are the connections we're going to make. I mentioned them before. Black connects the ground on the ultrasonic rangefinder to the ground on the Uno. Red connects the VCC on the ultrasonic rangefinder to the 5-volt on the Arduino Uno. Once you've got those two wires in, your ultrasonic rangefinder is getting power. The yellow wire connects the echo pin to digital pin 7. The blue wire connects the trig pin to digital pin 6. Oops. So once we've built this, we're going to do a very simple experiment, and we picked this experiment for two reasons. One, it's actually useful, and the second is this is an example of low-hanging fruit, how we can use this topic to cover topics that we cover in our standard syllabus. So one topic that comes up over and over and over again is linear functions. And in this particular case, time is a linear function of distance, so it's a great place to do this. So notice that in a math class, you might give students 25 problems exercising their skills at linear functions. And they get kind of boring. And once they're done with them, a month later, they've forgotten it. What happens is this topic is going to, because it's an essential topic, this topic is going to come over and over and over again in a natural way. So students are going to do this over and over again, and it'll be part of their toolkit. So what they're going to do is they're going to put the robot's wheels on we have a track that you print out with a piece of paper. On that track, there's a line that's marked wheels go here. You put the robot's wheel here. You take a target. You put it at a mark that's 5 centimeters away from the wheels, and you record a reading. How long did it take the sound signal to go out and bounce back? And then you repeat that over and over and over again. In class, we'd actually have students do this with distances from 5 centimeters to 6 centimeters. In the presentation, actually, we only did it for 3 just to shorten the time. So based on that work, what we'd ask our students to do is to find a linear function that relates time as a function of distance in the usual form. Time equals slope times distance plus b. So very standard problem that you see in lots of courses. You could do this if they're studying linear regression. If you've got 15 or 16 measurements, use linear regression. If you're just studying functions, linear functions the first time, take 2 points and use those to estimate the slope and the y-intercept. But then we ask some additional questions. What do the m and the b mean? So there are 2 parameters, a slope parameter and a b parameter. In this context, interpret those mean. Now, what we really care about, if you're building something to stop your car when it gets close to the back of the garage, you really want distance. So let's take that data we've got here and invert that. Let's find another function that gives us distance as a function of time. Now, if we're actually building the robot, at this point the students would stop and they'd change their program a little bit. So instead of displaying time, it would display distance. And that's an important step in the process of giving your robot some capabilities. But now let's get back to this idea of intellectual integrity, intellectual rigor, and making sure you've got a solid solution. When we did it, we used a nice simple target, maybe the flat of our hand or a book, and that worked really well. But how big does the target have to be? You don't have to worry about with the garage wall because you've got a big garage wall, but it's interesting to know if your target is smaller. So do some experiments, try smaller targets and see how well this works. The other thing that makes a difference is if the sound wave comes in and hits the target flat on. If the target is flat and it hits it at a right angle to the target's plane, it's going to reflect better. Just as if when you hit a tennis ball against the wall. If you hit it against the wall flat on, it's going to bounce right back. If you hit at an angle, it's going to bounce off at an angle. So how sensitive is this ultrasonic rangefinder to the angle of the target? How about different targets? Try it with a tennis ball can. Try it with, in my case, the back of my garage is obstructed by a ladder. How good would this be at detecting a target like that? So we ask students to go beyond just a simple mathematical exercise. Okay, I want to shift gears here, and I want to pose a thought problem just to think about. One of the most interesting things, one of the most important things we do is we control access to some place. And one way to do that is to have a sentry, and that sentry is standing there at an access point, and that sentry asks for some credentials. If that sentry says it's okay, the sentry is going to let you pass. That kind of duty is dangerous, and it's also boring. And when you've got that combination, it's a very bad combination because it's easy to kind of lose your edge if you're bored for long periods of time, and that actually increases the danger. So this is an ideal situation for a robotic sentry. And you've all seen things like this. Often we use them to control access to parking garages, where what happens is you drive up to a gate, there's a sentry at that gate, maybe you slip an ID card in, maybe you slip in a credit card, and then the gate comes up and you're allowed to go through. So we're interested in something like that. And the intent is that a good guy is going to drive up and stop at that sentry position, insert their credentials, wait to be allowed to pass, and then the gate goes up and they're allowed to pass. But what we're worried about is we're worried about a bad guy, somebody who drives up and crashes right through that gate and goes on and does some damage. They've gained access to a place they shouldn't do. And that's what we're worried about. So what we're going to do is we're going to think about how we might use something like that ultrasonic rangefinder to alert us and take defensive actions if it looks like the approaching vehicle is going to crash through the gate. So we're going to give our robot, our sentry, some artificial intelligence, and that artificial intelligence is going to get information about how far away the car is, the approaching vehicle is, at each instant of time. And based on that instant of time, that robotic sentry is going to have to make a decision. Does that robotic sentry take defensive action of some sort, or does it not take defensive action? So this is the kind of decision we face all the time. In medicine, for example, you may take a test, and based on the results of that test, you have to decide whether to start taking medicine or maybe undergo a second procedure. So we're interested in two kinds of errors. One error is a false positive. That's when our sentry, our robotic sentry, thinks this is a threat and takes some kind of defensive action. That defensive action could be a range of things. You could actually blow the car up. That's pretty extreme. You might raise some tire shredders. That's not quite so extreme. You could just sound alarm and flash some lights. Okay, that's very much like what happens in the medical field. You take defensive action, and that defensive action might have different costs, maybe because it's invasive or dangerous or expensive. So we're worried about false positive. We're very worried about implementing a defensive action when we shouldn't. The other thing, of course, we're worried about is a false negative. That's failing to take defensive action when we've got a real threat. So we have to worry about those two kinds of things. And that's a really good discussion. So we're having that discussion in this context of artificial intelligence, but it applies very generally. In fact, if we've got soldiers that are deployed, we often talk about rules of engagement. And those rules of engagement are exactly like this. They're the rules for when you take defensive action, when you take some action based on the current situation. So in a math class, we might look at some graphs like this. These graphs actually show what the approach of a friendly vehicle would look like. On the top, you're seeing how far that vehicle is from the sentry position. On the bottom, you're seeing its velocity, which is actually negative because it's going from right to left. And in this particular case, when the car is roughly 325 feet away, it starts braking, it brakes steadily, and it comes to a stop right at the sentry position. So that's a normal thing. Now, this is a good place to ask students to red team it. So draw some graphs like this that show what an attack might look like. So, for example, you might expect an attacking vehicle to slow down for a while, trying to look normal, trying to look friendly, and then to mash the brake, mash the accelerator, and speed up and crash through. So it's a good chance to talk about the relationship between graphs and what they're representing. Okay, I'm going to shift gears now, and you may decide to skip this. This is another device, and just to give us some examples. On the left, you see that Arduino Uno, and you'll notice there's that same LCD panel that we saw before, but up on the left there, up toward the right, you'll see a little tiny chip, and that little tiny chip has two capabilities. One is that it can detect acceleration, and we use that actually to detect the force of gravity, and that's useful for determining whether something is being held level or not, whether something's at a tilt. The other thing it can do is it can measure the Earth's magnetic field, and we use that to produce compass directions. If you got a mobile device, an iPhone or an iPad or another brand, you probably have a little application called Compass, and it looks like it does on the right, and it actually will show you due north using a sensor very much like this to sense the Earth's magnetic field, and another sensor is actually a floating hairline in the middle that you use to determine whether you're holding it level. Very, very useful. Mobile devices use that all the time to determine how you're holding them. So that's, for example, if you're, one of my favorite apps is called Starwalk. You hold your iPhone or your iPad up, or an Android device, and you virtually look through it at the sky. And it knows where you are, it knows what time it is, and because of this chip, it knows how you're holding it. And it shows you the sky as it looks to you with the stars labeled. So it's great if you're looking for constellations and stuff. Here's what this thing looks like up close, that little chip, and you notice it's got axes marked. So you'll see there's an x-axis, a y-axis. The z-axis, it's got that little dot that indicates it's coming out toward you. So it's a great thing to look at if you're teaching a multivariable calculus course, for example, and you want to talk about vectors, or a physics course. It brings up lots of topics. You can talk about gravity and acceleration. This is actually an accelerometer. It measures acceleration. So if we're using it for a spaceship out in space where there's microgravity or close to no gravity, it wouldn't feel anything. But what it does feel is acceleration. Gravity feels like acceleration. There's a little hint of the theory of relativity. So we can use that accelerometer, that acceleration measuring device, to essentially tell us where the force of gravity is. Good place to talk about magnetism and compasses. Good place, again, to reiterate intellectual integrity. If we were physically here, you'd actually play with this thing and you'd see it works. Works great on a desk. How does it really work in the field? Suppose you want to put this on a robot and use it to give that robot the ability to sense its north, south, east, west. Well, it's really sensing magnetism, and so you have to worry about magnetic fields. Our robot has a couple of motors, and motors have magnets in them. So one of the things we do is we'd experiment. We'd hold that sensor close to the motors and see how that affects it. Great place to talk about position, velocity, acceleration. Great place to talk about feedback and control systems. So I'm going to close this with just some open discussion questions that you might want to think about. So think about how we're using robotics and artificial intelligence right now, and think about all the questions that brings up. So the first question, should price optimization be outlawed? Is it really fair that the price you pay for an object is based on things other than essentially the cost of delivering that object, the cost of building it and delivering to it? How about self-driving cars? Over the next 5 or 10 years, we're going to make a lot of decisions about whether self-driving cars are allowed on public roads. The law now, the self-driving cars, you read all the time about cars driving across country, self-driving cars. There's actually a human driver behind the wheel, and that human driver is ready to take over. So as of now, we're not allowing completely self-driving cars on the roads. We're going to have to decide whether we're going to allow that, on which roads, how much. My guess is that in about 10 years, that question is going to be turned topsy-turvy, because what we're going to discover is that self-driving cars are actually better than legacy drivers. That's you and me, human drivers. And so the question is, to what extent will legacy drivers be allowed to share roads with public roads with self-driving cars? Would you like a robotic taxi? Are they a good idea? How does that affect the economics? How does that affect cab drivers? Is it still a good idea? Who should be liable if a self-driving car is in an accident? Is it the person that put it into self-driving mode and is now talking to people in the back seat? Is it the person that bought the car? Is it the person that built the car? Is it the person that programmed the car? How do we handle insurance for self-driving vehicles? What's the future of education with artificial intelligence teachers? So most of us here are educators, and one of the things we're interested in is the use of artificially intelligent driven tutors of some sort. Can that kind of tutor replace us? Let's flip that on the other side. There's actually a very interesting article in a recent, so this is being recorded, I guess on the 1st of August, 2015. Recent means just last week in July. There was a very interesting article in the Atlantic, and it talks about the future. The title is A World Without Work. So it's possible that as we are increasingly able to use robots to do the kinds of work that we do, there's going to be less work to go around. That might be a good thing. What if, on average, it only requires 20 hours of personal work for us to do all the things we do that are necessary now and in the future for us to live a pretty good life? That sounds pretty good. It might be very good if we all get to work 20 hours. It might be very bad if half of us work 40 hours and the other half without a job. So we have to think about that. As we get more time, can education be one of the lifelong things that we do that kind of replace work, that help give us a sense of worth, that help drive our civilization forward? One of the things you often hear about is robotic caregivers. So we've all seen the ads on television for a device where if you fall, you press a button and it summons help. How about robotic caregivers that can make it easier for people to live independently without moving in with their kids, without going to a long-term care facility? Might be cool. Is that a good idea? Do we really want robots replacing you in contact? How about robotic police? There's been an awful lot in the news lately about how police interact with people, and robotic police have some advantages. One big advantage of a robotic policeman is it doesn't have to worry quite so much about self-preservation. So robotic police, more generally robotic first responders, might be an interesting application. So what I'd like you to do in closing, well, not quite in closing, is to think about those things, talk about those things, think about how those kinds of questions might be integrated in our curriculum, and how we might talk about how we could use science, math, engineering, technology to build robots that actually improve our lives. And I want to close with this last slide. It's got our names and it's got our email addresses on. So please, love to hear from you, love to talk about these ideas, and thank you very much for your time.